No intro and all that. Sorry. Let me see. Share.
Recording in progress.
Oh, okay. You all have to both mute the microphone as well as the speaker. Yeah, now that there's no feedback. Let's see, share. Okay. So unlike yesterday, since I was editing the presentation till the very end, I haven't posted the link, but I will post it later. Let's see. Literally, until a few minutes before CNC showed up at my home, I was editing this. All right. Okay. So let me get rid of this floating window. Okay. Good morning, everyone. I don't know how many of the people that are currently in the session were around yesterday. I noticed it was 73 or something, right? Oh, it is increasing. Okay. Should we wait for a minute or two? Okay. Oh, yeah, that's true. Okay. Okay. This is a talk that is not in as mature a state, if you like, compared to the talk I gave yesterday on AI. I have given this talk only once before, and that was during the seminar course at National University of Singapore earlier this year. So you see the bullet here, the third bullet, where I talk about the fact that some of the material here comes from papers, and the papers are in this list at the link you see over here. Okay, all these are links that you can click on when you're looking at the PowerPoint slides in the slideshow mode. As I say here, not all the material that I've picked up from the other places has been appropriately acknowledged, and links have been put. So as I go along, I'll be fixing up some of that. So do keep track of my future presentations, because I will be giving this presentation with more material and better presented and all that the next few weeks. In particular, I'm going to give it at Indian Institute of Science as well as at Microsoft Bangalore. Those things will be on the 5th of January and 3rd of January, physically in Bangalore. Also, you all can find out about my various social media handles from my homepage, which now has been hosted in the Digital University in Kerala. It used to be hosted in National University of Singapore, but that account will disappear soon. So I had to find another place where I can do this sort of thing. Not being employed as a regular person by anybody introduces these complications. So in the last week or so, the Digital University Kerala, on whose board of governors I'm a member, they've been very kind in giving me the privilege of using their system to store my materials. So that's why the link to yesterday's presentation is actually to their web page where it's hosted, their website and so on. So pardon me for not having this presentation in as complete a form as I would have liked to. So in terms of the history, before I get into cloud databases, I wanted to talk about actually database technology in general and how it all evolved and so on. So I've had the privilege of being in the IBM research lab in San Jose in Silicon Valley in California for 38.5 years before I retired at the end of June last year. So from essentially almost exactly 40 years ago, December 28, 1981 is when I joined IBM Research. And that place is like Mecca for Muslims. It's like mecca for database people, in the sense that it's the birthplace of relational databases. For a couple of years after I joined IBM, one of my colleagues was Ted Cord, Edgar Cord, as he's called, who is considered the father of relational, and he got the Turing Award for that, which is like the equivalent of Nobel Prize in computer science. ACM gives this award. I talked about it yesterday in the context of AI. But he himself was more of a theoretician than a practically oriented guy. He was a British guy. He's no more. So there were other people, including the manager that hired me, my first manager, Patricia Selinger. She's considered the mother of cost-based query optimization. So there were people like Kerr and Don Chamberlain and so on, who were the people who brought to practice the theoretical ideas of Ted Cord. And those things were done in the context of this project called System R for relational. And it's in that context that Don Chamberlain, who is still alive, but the other person, Ray Boyce, who sadly died even before I joined IBM. He was very young when he died. A couple of years after he did the SQL language development, he had an accident and died. And so at the same time, when System R was being done in IBM research in San Jose, across the bay in Berkeley, University of California at Berkeley, Mike Stonebreaker and his colleagues were building a different system, which was called Ingress. And unlike the IBM one, they chose to come up with their own language, and it was called Quell, Q-U-E-L, as I've written here. While the conceptual model underlying these languages was the same, namely the relational model, the APIs were very different. And in terms of power and all that, also they had different features and so on. So obviously, as you can imagine, there was a battle as to which one will be the one that will survive in the long term and such. So in the battle for standardization, IBM guys won out. So the ANSI standard and the ISO standards and all that in subsequent years decided to choose SQL as the basis for the standard. Of course, the language evolved and there were some conceptual bugs and all that in the way the IBM guys had done. So as part of the standardization, and many other people got involved from other companies, universities, and so on, the language got refined. And one of the guys that was there in IBM research that left IBM before I joined, who was very well known even as I joined IBM and subsequently became even more famous, was a guy called James Gray. Much later, compared to Ted Cord, he also got the Turing Award because he was a guy who was working on transactions and related topics. And I became essentially his replacement a year or so after he left to do transactional work in the context of what was then called the R-Star project, which was a follow-on to the original System R project. I joined that R-Star project, which was a distributed database version of System R, midway through its lifespan. That project started around 79. It ended around 83, and I joined at the end of 81. So it turned out many, many years later, more like 18 years after Jim Gray got his Turing Award, Stonebreaker also got the Turing Award for various pieces of work he had done. Unlike Jim Gray and Ted Cord, Mike Stonebreaker being a faculty member at Berkeley, and later on he retired from Berkeley and went to MIT as an adjunct professor. He had done many things in addition to being a professor and producing PhD students and writing a lot of papers. He also turned every one of his projects, prototypes, into a commercial offering by starting companies on the side and things like that. So over the decades, it turns out, in spite of various attempts that have been made by the more modern day kind of youngsters who thought many things were wrong with SQL, blah, 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 and they came up with this concept of NoSQL and big data and MapReduce and Hadoop and all this kind of stuff. where they initially threw out a lot of the important features of SQL. Later on, they realized the follies of their ways, and they had to reintroduce the high-level language concepts that were the underpinning of SQL back into the MapReduce kind of frameworks and even the NoSQL kind of languages, which were all highly non-standard and things like that, MongoDB and various other such systems that got developed. I'm not going to spend time focusing too much on any of that stuff. I have other presentations where I talk about the big data ecosystem and NoSQL and what's wrong with them and why they came about with supposedly legitimate reasons, but in fact, a lot of those reasons were not quite well thought out and things like that. You can look at other presentations. So if you look at a traditional database system, a single node database system, it has various components. So there is the concept of data definition as opposed to data manipulation. Data definition is the way in which you create tables and indexes and modify them over time and so on, the metadata. And there are catalogs which store information about what tables exist and how many columns they have, what are the columns types and all that sort of stuff. And then you have, separate from that, the modification of the contents of the tables, even things like data definition operations that involve dropping tables and even doing things like backing up the table content and so on. But the thing that ordinary people will do will be more the DML operations as opposed to the DDL operations, which are the data manipulation operations, which are in SQL terminology, it's doing a select where you are retrieving data based on certain conditions being satisfied by the data, and also doing things like insert, update, and deleting of the rows or records, whichever terminology you like. Is somebody? Oh, one of you. Okay. If you look into the architecture of a database system, it has a compiler that does the parsing of these SQL statements, and there is an optimizer. One of the major features of relational compared to pre-relational systems is the fact that in the case of the pre-relational system like IMS, which was an IBM system, which had the hierarchical data model, there you had to write programs in order to access the data. You didn't have a high-level language like SQL over there. The language there was called DL1. It was an API, but you had to write lengthy programs, and you as the programmer who is accessing the data had to know when you should do a complete scan of all the data to retrieve the ones of interest, or when you should use a particular index that might exist against that data. And there were different types of indexes and so on. So you, as the person who wants to manipulate the data or retrieve the data, had to know a lot about the internals of how the data was stored and what kind of access structures were there. But the goal of SQL, and hence its popularity from a productivity viewpoint and all that, was to insulate the application programmer from not having to know about the details about how the data is being stored and what is the best way of accessing the data when there are alternate ways in which you could get at the data. All of that, just like you have in the programming language space, assembler language or machine language way of writing a program versus writing a high-level language like using Fortran or PL1, or in the modern days, Java and various other languages that have come about in the meantime. For some of the older people, Pascal and such things, right? Basic and such languages. What were the benefits of those high-level languages? It's the same sort of principle behind SQL, how to make data retrieval and data modifications operations be performable without too much internal knowledge and so on. So it's in that context that there's lots of componentry within the DBMS architecture that deals with these aspects like query optimization, query planning, query execution, monitoring the execution of the query, and potentially even changing the execution plan based on observing that the assumptions that were made in doing the optimization are in practice not turning out to be true, and so on and so on. So I don't have the time to go through all this, but the notion of transaction was introduced, and you could do multiple operations within a transaction. And if the system crashes anywhere in the middle of that execution, all of the changes that had so far been done within that transaction will get undone. So the notion of atomic transactions and such were also introduced. These are the sorts of things for which Jim Gray became popular initially, but then the Mohan of Tamil Nadu got into the picture, and he did some stuff like the Aries recovery method and so on. Some of that was mentioned in yesterday's introduction. So my claim to fame was to improve upon this concurrency control and recovery and all that, how to deal with failures and how to deal with the people in parallel trying to do things, but still making sure that they don't step on each other and mess up the integrity of the data and things like that. So there's lots of things I can spend time discussing those aspects in gory detail and put you to sleep, but I'm not going to do that today. So let me just say that the reason behind giving you this introduction to the internal architecture of the database is to say, once you get into the distributed environment or the cloud environment, some of these components, which used to all execute in a single node, in a single node database system, had to be then split across different nodes and so on. That's what made the move to even a distributed context, and now more recently to the cloud context, all the more, depending on your viewpoint, complicated or exciting to work on and innovate and all that kind of stuff. So it really is a question of where you come from as to whether you get turned on by this or you are put off by it. So in the spirit of further amplifying what all comes into play in the cloud context, it's also important to talk about where the persistent data gets stored. So if you look at this picture, you see at the bottom data files and data dictionary, and the thing that's at the bottom is the disk drive. And there are various kinds of disk drives. And also, even in the case of memory, there are different kinds of memories, registers and cache memory and all that. So that's what this picture is trying to communicate. There is a storage hierarchy. Sometimes when people say storage, they only think of non-memory components like flash disk and traditional hard disk drives, which are magnetic disks. And then they also talk about tape drives. And tape drives are still alive. Many people think that all these old technologies that the Mohans and the CNCs of the world dealt with in their IIT days have all gone away from Earth. No, even COBOL hasn't gone away. There are lots of things that the TCS and the Infosys and all these kinds of people, even IBM, global business services kind of people that work on, that relates to decades old, existing pieces of software and such that power a lot of the world's, day-to-day, highly important transaction processing systems and such. Sometimes people think, these days, oh, if Facebook goes down for a day or Google goes down for a day, all hell will break loose. Guess what? There'll be even more economic damage if the IBM systems of the world stop working for a whole day. The youngsters don't realize how much the unfashionable thing that powers the whole world's hardcore, bread and butter transactional stuff is important. They all get carried away with all the flashy stuff that the, gadgets and all that you and I carry in our pockets, as if those are the most important things, and they are not actually, relatively speaking. You might think, yeah, if you can't order something on Amazon today for delivery tomorrow, it's as if, your life has become miserable and so on, but that's not as important as things like trains operating and so on, right? So the banks, ATMs operating and such. So one of the important points to keep in mind as you look at this picture is to realize that as you go from what is close to the computational hardware part of the computer, namely the registers and caches and main memory, go down, the capacity increases, hence this pyramid shape, but also the speed at which you can get at the data that's stored at these various levels gets worse and worse. But the cost also is an interesting thing to look at. The registers and the cache memory and all that are very expensive on a per whatever the unit is, byte or word or whatever, or megabyte or gigabyte and such, compared to the slower media where for the same amount of money, you can get a lot more storage. So along with all this also comes the notion of other disks attached locally to an individual node's computer, meaning the CPU and cache memory and such, or is it actually across a network? So the storage being across the network might mean that multiple computer nodes can all have access to the same disk storage and such without having to go through yet another node to get at it. Meaning you distinguish between data storage nodes and computational nodes where like query processing and application program execution and all that can be done. Anyway, some of this might sound like gobbledygook, but as time goes on, you'll figure out. So this is just to show that, in the previous one, it only talked about remote secondary storage. It didn't go into some of the details. So whereas here you will see that tapes are mentioned, distributed file systems are mentioned, web servers are mentioned. And it also is the case that in terms of persistence, if the power goes away, things in the registers and the cache and main memory will disappear if it's DRAM. But if you have non-volatile memory, things like the Intel, what is it called, Optane and such. Is it Optane? I forgot now the name. That is byte addressable memory like DRAM, but it's persistent. So even if the power goes away, whatever is stored in it will survive that power failure. But traditionally, until this notion of byte addressable non-volatile memory came into existence, NVRAM as it's called, it's only the magnetic storage and the optical storage that was persistent. But then came things like SSDs, which were also persistent, but they are page addressable or block addressable. And there are various other characteristics that I just don't have the time to go through. But in terms of the way in which the data gets managed, you have the notion of block-oriented storage versus file-oriented storage. The APIs that you use to get at the data and where they get stored and the cost of that storage varies quite a bit, and some of the information is given here as to what the situation is. So there is notion of object-oriented storage versus file-oriented storage versus block-oriented, and some of these sorts of things will also differ with respect to what kind of storage is used to house them, whether you use magnetic storage or optical storage or tape storage and things like that, and also how far away they are from wherever the data might have originally been generated. So the amount of time it takes to get at something that might even be offline, because some of the tape contents might be sitting in an unmounted state, and a robot goes and grabs the tape and then mounts it so that it becomes accessible. So those things obviously take orders of seconds, if not minutes. Whereas things that are already online, you can get at it in tens of milliseconds, for instance. And of course, in the case of things that are in DRAM and such, it's microseconds and such things. And so there's lots of things. And also in terms of the reliability of the storage, the properties vary across these different types of things. And then we also get into this whole business of whether the data is stored in an encrypted form or in an unencrypted form, and what that has, what effect that has in terms of speed at which the data can be unencrypted and things like that. Whether you can also even process queries against the data in its encrypted form itself, which is the kind of stuff that the IBM guy discussed day before yesterday. Yeah, there's all this, what was it called? Homomorphic encryption and doing computation without the data being unencrypted and so on. So let's now go on and look at different kinds of workloads. The famous thing that used to be the focus for a long time, especially with the pre-relational systems, was your bread and butter, short and sweet kind of transactions, which had to do with buying tickets for a flight or a train or doing inventory management and things like that, which were the areas in which transaction processing systems like CICS and IMSDC and such used to be very good at. But they were not good at report generation and ad hoc queries and so on, because there you had to write lengthy programs and you had to know lots of innards and so on. So OLTP represents online transaction processing. And this is where even the ATMs that used to be powered for a long time in a very fault-tolerant way by systems that were produced by Tandem and such companies used to excel in. Then came this notion that, oh, you know, the C-suite guys, the CEOs and the CFOs and CMOs and so on, they want to know how the business is doing. They are not so much interested in the nitty-gritty aspects of OLTP, but they want to know what is currently popular and how much sales did different people make and what's the revenue and so on and so on. So they had to get an integrated view of these individual transactions activities by summarizing the data and things like that. So that's when, especially with the advent of relational databases, which made it easier to post such queries and also get the queries processed efficiently and without much effort on the part of the programmer, this OLAP became very popular and, you know, easier to do, and people were able to get these queries formulated as well as executed much faster than they could do in the pre-relational systems. And so typically for these sorts of workloads, there used to be two different systems, one focused on OLTP and another one focused on OLAP. And the data that the OLAP guys wanted to process was actually produced by the OLTP system. And so you had to have this notion of a warehouse, and the data got moved periodically from the OLTP system into the OLAP system so that the more recent data can then be queried upon and so on. So this introduced its own complications, which I'll very briefly touch on. But subsequent to this, various requirements came, which required merging the concepts of the OLTP and the OLAP system so that the queries can actually be on the latest and greatest state of the data rather than on a snapshot of the data as of some time ago, which is what the warehouse approach allowed you to do. So this HTAP concept was a combination of OLTP and OLAP, and that acronym stands for Hybrid Transactional and Analytic Processing. How to have just a single copy of the data and let both kinds of workloads go against it. And there are complications here because the OLTP guys have stringent response time requirements, whereas the OLAP guys, because they are looking for trends and this and that, from a correctness viewpoint, as well as how long it takes to get the results, OLAP is more a luxury than OLTP, which is your bread and butter money-making thing. And so for such reasons also, you don't want the OLAP, which might take a long time to execute and highly resource consuming, preventing the OLTP transactions from executing with the stringent SLA requirements that you might have, response time, guarantees that you have provided. And if you violate those guarantees, you might be penalized and so on. So there's more details here. I shouldn't spend too much time on all this. OLTP systems, in order to compare different systems, benchmark was needed so that a fair way of comparison can be done across not only different software systems like DB2, Oracle and such, but also across different hardware platforms and different operating systems and such. So this is where the Transaction Processing Council got formed based on an initial thing called the debit credit benchmark that Jim Gray and other people cooked up. It had to be more formalized and so on. That's when the TPC got formed across companies and more stringent rules were formulated as to how to audit these benchmarks and such. And the TPC-B was like the more refined version of the original debit credit benchmark, and on and on. So there were various computer architectures that were proposed in order to realize an OLTP system, and that's where this notion of shared everything, shared this and shared nothing got invented, and there were lots of debates and rivalries across companies as well as research groups and so on. By the way, I didn't say it before. While my colleagues before I joined IBM invented the relational database technology as well as implemented it and came out with the SQL language, IBM's product people were not too eager to commercialize that stuff because they said the pre-relational system IMS is doing very well. Why confuse the customers by doing this paradigm shift and then having to explain to customers when to use IMS and when to switch to relational? And so they were dilly-dallying. Meanwhile, Larry Ellison and company read the papers produced by my predecessors, and they copied a lot of ideas, especially the SQL language syntax and semantics, because the papers written by the IBMers went into the details of all that. But the internals, they didn't have as much access to as to how the recovery and concurrency control and all that was done. So they did some things that were their own, but they commercialized the relational technology. And then the IBM research people who had been harassing the IBM product guys to commercialize it, they used this as ammunition, saying, what nonsense is this? We invested so much money and effort and everything, and now these other guys are simply taking advantage of it. You guys are stupid. You should now take the research prototype system R and commercialize it. That's how the first system from IBM called SQL DS came out on VM and BSE operating systems. A few years down the line is when on the mainframe MVS operating system, DB2 came out. That was super duper compared to this research prototype, which nominally got modified a bit and then got released as SQL DS. But much later came the other guys like Sybase and Informix and SQL Server. Indexing and all that was also an important thing to make these OLTP transactions execute really fast. And also Sybase, for instance, introduced the concept of stored procedures to make the client-server interactions be done much more efficiently, rather than every SQL statement requiring a round trip or even accessing one record at a time after you post a query, causing a message passing thing to happen between the client machine and the server machine, assuming your application or the end user is sitting at a client machine that's different from the machine in which the data is actually stored in the DBMS bulk of the software is running. So some of these things were intended to, instead of interacting at a very low level, put a whole program on the other side, on the server side, with embedded SQL in it, and do a bunch of local interactions that then involve network connections and so on, and then send back the result at the end of the execution of the program and such things. And also, over time, as new hardware technologies came about, like vaster amounts of main memory, DRAM, and then subsequently SSDs and such, and also even, whether you compile SQL down to machine language or you compile it down to some data structures which get interpreted at runtime, there have been lots of things here that I can spend hours and hours on that I don't know how many of the people are interested in. But in the context of OLAP, various ideas like data cubes and multidimensional analytics and data mining and decision support and such came about. And there were separate kinds of benchmarks that were developed, TPC-D and variations on it, subsequently DI, DS, H, and so on. Indexing here became trickier because if you have too many indexes, then the OLTP guys will suffer, because every time you insert a record, you have 10 different indexes on a table into which you are doing the insert. You have to spend a lot of time updating those indexes if you're going to do them synchronously. But for ad hoc queries, since you're going to look at a vast amount of data, not do a single record insert or delete or update or fetch, you want to do what's called a relation scan, go through the data in one pass and select what records are of interest. So it's okay to do some of this in a specialized way compared to how you answer OLTP kind of built-in selects and such. Anyway, there's a lot of detailed stuff that will take quite a bit of time for me to explain, but the important thing is that if your ad hoc query is going to go across vast amounts of data, gigabytes or even terabytes and petabytes and things like that, you don't want to restrict yourself from using a single CPU or a single node, even with multiple CPUs, multi-core node, but potentially use multiple nodes where parts of the data will be examined by these different nodes, and collectively they will look at vast amounts of data and they'll do it in parallel. So the notion of parallel relational database systems got introduced, and one of the pioneering systems in that space was something called Teradata, which came out of PhD thesis as Caltech. And later on, the single node DBMSs like DB2 and Oracle also introduced extended versions of their original systems, which leverage the concept of parallelism. And meanwhile, also, there was this notion of, oh, I would like to program in an object-oriented way, but these relational systems are doing things in a more a tabular way. So there was this notion as a result of going from an object-oriented way of looking at the data to then translating it to a tabular way. So this is where object relational systems came about. And so especially when Java got introduced and it had the object-oriented notion, in the front end, you'll operate on objects that are in transient memory, in main memory and such. But in the back end, the persistent version of the data is stored in a relational form. And so you have to do this constant remapping from one form to the other form. And as you modify the data in the object-oriented fashion using Java constructs, then when you write it back, it had to be transformed from the in-memory Java format to the serialized format in which it's stored on disk. So there was all this serialization and deserialization and all that happens, and also garbage collection, because Java is a language where you don't explicitly free objects and things like that. So there's lots of stuff that gets complicated with all of this. Meanwhile, also the new hardware features came out, things like GPUs and FPGAs and such, the leveraging of which resulted in these queries being processable much faster than just relying on traditional von Neumann CPUs, for instance. And so this just shows you that the notion of data warehouse that I mentioned before, where on the left-hand side, you have these different sources of data, which could come from CRM systems, ERP systems, and things like that, even from Excel spreadsheets. And then you want to now, on the right-hand side, as an end user or an application that consumes such data, you want to look at the data in a very different form. And also you want to be able to integrate the data that are in different repositories on the left side without having to worry about the details of what data is where and such. You want to pretend when you ask the queries on the right side as if all the data is in one location, and let the software in between worry about precisely how to take this conceptual view as if everything is one database, and in fact split the query taking into account metadata which says, oh, this portion of this conceptual data is in this system, maybe it's in a CRM system, but this other thing that's made to appear as if it's the same system is actually in a financial application. And so this is where you get into this notion of heterogeneous data integration and query processing, which deals with this heterogeneity in various interesting ways. And in between, you have this notion of cleansing the data, because the same data might be stored in multiple places on the left-hand side. You know, Mohan might be described with certain attributes in the ERP system, but Mohan is also described in the CRM system with some overlapping attributes and some other attributes which are not present in the ERP system. And by the way, when I moved from one house to another, the ERP system's version of my address got updated, but the other one didn't get updated. So you have mismatches and all that. So all of that kind of stuff needs to be worried about. And meanwhile, with all this emergence of big data and such, especially in the context of social media and e-commerce and so on, people said, oh, storing all this vast amounts of data in a relational system, which requires data to be in a certain format and things like that, is too time consuming. And a lot of the data that gets collected, we don't know whether we'll make use of it ever, or in what way we might make use of it. But would it be nice if I store the data in the raw form in which gets collected? And that's how this notion of data lakes came about. And can I now manipulate the data even as it's stored in the file systems in the raw form? And this is where complexity comes in, because when you store the data in a raw form, you don't take the trouble to document the format of the data and so on, what assumptions went behind what got stored in each field, and various things that over time might get forgotten about because you are not being disciplined in documenting everything about this file format and how to interpret the different fields within this records in this file and so on. So a lot of this has to do with this garbage in, garbage out kind of thing, and a data lake could become, as they say, data swamp, because you don't know anymore how to interpret the data content, because the data is not necessarily self-describing. Whereas in the more traditional method to the madness way in which things got put into relational databases and such, there were all these catalogs and such that forced you, also with data integrity rules and all that, referential constraints and domain constraints and triggers and such that were there, that also ensure that when the data got into a relational DBMS, based on the rules that were set up by the database administrators and such, the data schema designers and so on, that things were in a form that they could be easily processed, and the meaning behind the data could also be figured out and things like that as the queries are asked and such. So this is a lengthy discussion to get into, but this is where Hadoop and subsequent to Hadoop, Spark and such came into existence. And that's still an evolving field. And that's where I said, to begin with, when the MapReduce notion was invented by the Google guys, which by the way involved one Indian guy also, these two guys, Sanjay Gamawat was the Indian guy, and Jeff Dean was the non-Indian American guy. These guys got some fancy prizes, including the Infosys prize in computing, which is now called the ACM prize in computing. They don't associate the name Infosys anymore with this award that the ACM gives out. So while it was good for the geeky types in my backyard in Silicon Valley, who are smart ass people who are highly paid and such in these social media companies, these hard to use kinds of things, who have a lot of times even PhDs, at least masters and such, and they are not your average Joe Blow programmer or even DBA in your Main Street America, Main Street India kind of IT shops. So they got too carried away, these geeks, 20-something geeks, in thinking that whatever suits them will suit the rest of the world's mere mortals in the IT area. And that's where I said they threw the baby with the bathwater by not focusing on high-level concepts that were part of the SQL language. But over time, they realized when they wanted to actually make money as opposed to just producing open source software and making it available for free, as Hadoop was, they had to address the people whose requirements they were not addressing, but who are the people who are likely to actually pay money. Those are the traditional enterprise customers and so on. And that's when some of the things that were not thought as being important got reintroduced. So that's how these big data systems or the NoSQL systems actually started supporting SQL. So much for things like Couchbase being called NoSQL, but they are proud now that they are supporting SQL as an access language. So along these directions came this requirement for combining in a single system supporting of the OLTP and OLAP so that your queries will be operating against the latest state of data, not some snapshot version of the data that might have been the state as of last night or 2 days ago, or depending on how often you populate the warehouse with the latest version of the OLTP database contents. And there are performance implications and all that of all this kind of replication and so on. So this is where this HTAB concept came about. Along with all this also comes this notion of trade-offs that you have to engage in, which has to do with consistency of the data being maintained, as well as the availability of the data being maintained, while the network might undergo partitioning, where when you have a distributed database kind of environment where parts of the data are in multiple nodes, and there may be replicas, there may not be replicas, but the data is so huge and you want to leverage multiple nodes processing capability that the single database gets split into multiple pieces, shards and such the terminologies that are used, and they are managed by these different nodes. And we'll get into this shared disk versus shared nothing and so on over there. But the important point is there are weak links along the way, which are the network links that connect these different nodes. In each of the individual nodes might be highly reliable, but the network connections may be flaky and the bandwidth may not be good and things like that. So because of all that, there are times when some nodes may be inaccessible, either because the nodes have failed or the connection to the nodes have failed. And so under those conditions, the question is, are you going to prevent somebody from being able to modify the data because that piece of data has 2 copies and currently only 1 copy is accessible? And are you going to later on go and fix up the other copy? Or are you going to say, oh, I don't want to allow this to happen at all, this update to 1 copy, because who knows, maybe the other node is up, but I'm not able to talk to it. And in parallel, somebody else is modifying the other copy. So you'll have then an inconsistency. But at the same time, people might say, hey, availability is more important than consistency being maintained across copies, or even if they're not copies, if it's the case that the value of A plus B should also always be a constant value, and you are modifying A, but you can't now look at the value of B because it's in some other node. And Chandri in this other node might be in parallel modifying B, and I'm modifying A. But this validation to ensure that these 2 modifications are still resulting in the A plus B value being a constant cannot be performed because we are unable to communicate, things like that. It's also the case that this has an analogy to what's called the split brain syndrome, where even in the human brain, there are times when something could go wrong whereby the brain gets split into 2 parts and they are unable to communicate with one another. And so this leads to all sorts of real world problems. But the same sort of thing also happens in the computer networking and the database context, where if you let multiple subsets of the distributed system continue to operate, where each connected component is thinking that's the only guy in town or that's the most important thing, and the other also in parallel thinking they're also equally important, then you could wind up doing things which later on cannot be reconciled. and humans might have to get involved. In not all cases can such concurrent parallel activities that got done when these subsets of nodes couldn't communicate with one another could be handled in a programmatic fashion. And you might have to take tweezers and go and fix up the data and so on if in fact they were interested. So I'll skip through some of these things because how am I doing with time? Okay. Okay. So there are various issues with these HTAP systems because it turns out the original way in which data was stored was each record was stored in a contiguous fashion, meaning all the different fields of a record got stored continuously, whether it's in memory or on disk. So each record in its entirety was stored in contiguous storage, and then the next record will be stored. This is very good for OLTP, but for ad hoc query processing, and where you might not be interested always in everything that's there in a record, even if the record qualifies, but you are only interested in subsets of the record's contents, it might be better to store the data in a columnar fashion, where across different records, column A's contents are clustered together, and column B's contents are somewhere else clustered together, and so on. Or you can even actually take multiple columns that constantly keep getting access together, like the street name, the town name, the state name, and the zip code. They are always going to be accessed together, but they are stored as multiple columns. You might choose to store the address, which is a combination of these different columns, in a clustered fashion. And so, again, this will require more time to get into the details of. So there's this notion of columnar storage versus row storage. And there are specialist systems that have been developed which do one thing or the other thing very nicely. And this is where having a warehouse where for the OLTP part, you store the data in a row fashion, but for the warehouse part, you store it in the columnar fashion, will allow for certain efficiencies to be gained. But then the pain is the warehouse is out of date with respect to the OLTP version of the database. And so if you want to have the cake and eat it too, meaning you want to be able to do your analytics on the latest state of the data, now you have to wrestle with this problem of how do I combine this row orientation versus column orientation in an interesting way. And that's where the HTAP systems have done some very innovative things, like to begin with, when the OLTP way of putting in the data does it in a row fashion, the data will temporarily be stored in the row fashion. After a while of collecting a bunch of these record-oriented, newly inserted data and newly updated data, then in a batch-oriented way, you will convert those pieces of data highly efficiently into the columnar version. And so sometimes you might have to combine the data when a query is asked by going to the row version of a subset of this database, and then post the query also against the columnar version and combine the results to produce the ultimate result. Anyway, so there's lots of things about all this that can be discussed in gory detail. As I said, in terms of how to efficiently deal with high transaction rates or high query rates with vast amounts of data having to be managed, where not all of it could be done in a single node, that's when the exploitation of parallelism and multiple nodes came into the picture. In the shared nothing architecture, what you do is each of the nodes has a portion of the database locally, in locally attached storage. And now what it means is that as long as you want to do single record kind of operations, it's enough if you access one node, but you have to now know the particular record of interest that you want to deal with, which node is the one that's the owner of that record. So you need some metadata that gives you that ability. But if you want to, in a single transaction, modify multiple records, and they happen to be owned by two different nodes or n different nodes, then in order to guarantee this atomicity, you have to do it in a distributed fashion and using something called two-phase commit protocol and all that, which I had a lot to do with That's also one of my, if you like, claims to fame or whatever. My very first project at IBM 40 years ago. But the alternative approach is to say, instead of storing the data locally and associating with each node a portion of the data and calling it the owner of that portion of the database, you now put all the data in a set of disk drives that are equally accessible from all the nodes, as this second picture shows. And now what it means is that any node can directly get all the data for reading or writing. But now there can be chaos, because node 1 and node 2 in parallel might retrieve the same data and in parallel modify it and then store it back. If you don't control this kind of concurrent access carefully, one node's update could get wiped out by the other node's update in a way that's not acceptable. So this is why we need to do what's called global locking, where across these nodes, you have to introduce certain message passing or certain interesting way of controlling concurrent access to the data. Whereas in the first scheme, in shared nothing, since a piece of data was owned by only one node, the concurrency control had to be done only within that node. And so local locking within that node was good enough. Whereas in the shared disk approach, you don't need to do two-phase commit, but with respect to locking, you need to do not only local locking, but also global locking. So that's the area I also had a lot to do with, where IBM introduced something to make that process efficient, the shared disk architecture, by having something called the coupling facility that I don't have the time to go through. And Oracle didn't have that to begin with, even though they were supporting the shared disk through what's called RAC, or Oracle Parallel Server, even before that. But we introduced this coupling facility and made things much more efficient in the IBM mainframe context. And later on, Oracle guys copied some of my ideas and introduced something called cache fusion. Some of you might know about these things. But in any case, to give you a historical perspective, the topic of distributed databases has been worked on for, believe it or not, for 5 decades. So even before I got into the picture, even while I was sitting in India, 72 to 77, doing my BTech in Madras, distributed databases were being researched on, but there weren't too many actual implementations. There were a lot of papers written, but it was really the system that I became involved in, called R-Star, as well as some other places where they were building distributed systems. Like there was something called SDD1 that was developed in the Boston area by a little company called Computer Corporation of America. And then there were a few other things also done in Europe and so on. It's these sorts of projects that were, at least from a research prototype building perspective, where the innovators, and later on came products based on some of these things, where they even dealt with more complicated scenarios than what we did in the research context. So in doing all this, you have to also worry about how to partition the data, which has implications on the sorts of things that I was saying before between row-oriented storage versus columnar-oriented storage. So the data in a single database gets partitioned, or even if you look at a single table, some subset of the records might be put in one node, other subset gets put in the second node, and another subset in the third node, and so on. That's called horizontal partition. You're taking a table and drawing lines, horizontal lines, but you could also go draw vertical lines and take some subset of the columns across different records to be stored in one node and other columns to be stored in a different node, and so on. And that's called vertical partition. When you are dealing with such a distributed network, you can also talk about what kind of failures do you deal with? Do you deal with only CPU power going away and hence the memory contents in the non-volatile, the volatile memory disappearing while the disk content is still intact? Or also, are you dealing with disk failures, which results in disk contents getting clobbered, where unless you take periodic backups of the disk contents, you won't be able to recover from such disk failures where the disk head crashes and things like that? And also, do you deal with network failures where connectivity between nodes fail and you have to deal with such? Now, one more failure that hasn't been dealt with that much in the past, which has become more important with the emergence of the internet, and also which gets talked about a lot in the context of blockchain, is this notion of Byzantine failure, where intentionally people go and screw up the database. They take over a node. This happens with all the hacking and so on, where they create bad things to come about, not because of any traditional kind of failure, but because of human maliciousness, right? So that's called the Byzantine failure. There are also all these notions of node autonomy and so on. So in any case, if you have the concept of table A exists in node 1, but you also want to have a copy of table A in another node, because if node 1 goes down, that's the only place where you have that table, then until that node is recovered, you won't be able to have access to it. So by replicating the data, you can increase the availability, but also that means that every time you modify something in table 1, table A, you have to also go modify the other copies. Whether you do those modifications of the other copies synchronously, meaning even as the transaction is modifying the first copy, you don't let that transaction finish until you actually go and in a synchronous way modify the other copies. That's called synchronous replication. But the bad thing with that is if some nodes are down and hence their copies cannot be synchronously updated, you don't want to prevent the transaction from completing. So if you now do asynchronous replication, then outside of the main transaction, which is doing an update, you go and modify the other copies. But that means that these other copies for a while will be out of sync with the primary copy in which the original update got done. And these all have implications similar to what I said before between OLTP version of the database versus the OLAP version of the database or the warehouse version of the database. And there are various techniques we all have worked on to do this replication in an efficient way, some of which could involve taking the log produced in the primary node and using that log to recreate the changes on the backup node, which can be much more efficient than re-executing the transactions. There are also situations where re-executing a transaction on the replica node might be more efficient than taking the log and transporting it. But there are also other implications that come from if you have any non-deterministic constructs in your SQL, like looking up the current time and looking at a random number generator and pulling a value, or assigning a sequence number for an order number or a part number. If you re-execute the transaction, the copy will get different values because that's being done at a different time and things like that. And that will lead to data inconsistency. So there's lots of these sorts of systems that are around. I won't go into the contents of these tables. There are relational databases, which are distributed databases that have been developed over a long period of time that have been done by different vendors and different research groups and so on. There are also NoSQL systems that have been developed by different parties. Here it talks about MongoDB, Foundation DB, and Apache Cassandra, and so on. Amazon DynamoDB, as well as Microsoft Azure Cosmos DB and things like that. They all have, certain things they are equally good at, and other things where there are differences in that. Now comes all this discussion about in the cloud context, what are the different kinds of cloud models, deployment models as they are called. You have the notion of a public cloud like Amazon and Azure and so on. Not everybody is happy with using the public cloud because of security concerns and hackers potentially getting at them. And no, I'm. Oh, they want? Okay. How do you ask the people? Hey, Robin, do you want to have a break now?
I think we can go.
Okay.
You have 1.5 hours.
Okay.
Yeah.
Okay, I'll do that. So within a big company, especially, you might have a private cloud which is like a slightly more evolved version than the on-prem computing, where even different units of an organization could have their own individual on-prem hardware, versus across different units of the same organization, you might have a centralized data center or distributed data centers and so on. That's a private cloud. And then the community cloud says, I want something in between, meaning a few companies that are working together might want to have something that's private to just that group of companies, but it's not private to just one of the members of the group. And then IBM more recently spent $34 billion acquiring Red Hat. And their value proposition is that in many enterprises, you want to be able to have, for various good reasons, bulk or certain portion of their data being stored and transactions being executed in the private cloud. But there are other pieces of data or applications where they are fine with using the public cloud. So you want to be able to seamlessly, from a programming perspective and all that, support activities that span both the public cloud and the private cloud. And that's what's called the hybrid cloud. So the value prop that a company like Red Hat, which IBM acquired, brings to the table is to say that they want to be able to flexibly support the hybrid cloud, where over time, something that was on the private cloud side could even get moved to the public cloud or the other way around. And the applications don't have to change. And furthermore, they also say, guess what? The APIs are different potentially between the private cloud and the public cloud. And guess what? Even in the public cloud, the different vendors' APIs and the functionalities are very different between, let's say, Azure, Microsoft Azure versus Amazon Web Services. So do you want to tie yourself up, get stuck with a vendor because you are using their own APIs directly in your application? Wouldn't it be nice if you use the more standardized APIs that the Red Hat guys have defined, so that over time you can change your mind? You could decide, for whatever reason, cost or some other reason, you're not happy anymore with Amazon Web Services and you want to move your data and applications to Azure Cloud. Or in parallel, you want to be able to have some of your data and activities going on in Amazon and others going on in Azure, and even others going on in Google Cloud. So how to concurrently support what's called multi-cloud as well as the hybrid cloud in a way where you have the freedom of movement and you are not stuck with any one vendor. And that's where it's in a way similar to the way SAP worked, SAP R3, where if you coded using their APIs, you had the luxury of the backend database system being changeable. For a while, you could be using DB2 as your backend, and for whatever reason, if you change your mind, later on, you could make the data get moved to Oracle without your application having to change because you're using the BAPL or whatever it's called. That's the SAP R3 APIs. So there are more details here that I'll let you go look through at your leisure. There are also these notions of cloud service models, which has to do with in what way are you going to use the cloud? Meaning you just want virtualized resources like compute power and storage and networking capacity, and the rest of the stuff you're going to deal with yourself. Or are you going to rely on the cloud provider to also give you the operating system and the middleware? And that's the platform as a service, as opposed to the first one, which is the infrastructure as a service. Or do you want to just use a piece of software in the cloud? without worrying about operating system and middleware, but you want to make use of the application software or package software that's running in the cloud. And there's actually an even more modern one, because if you look at this picture, this came from a website where, oh, why did this not? Which was done in March 2017. Okay, now, if you look at this picture, this is February 2021, there's yet another one called Function as a Service. Okay, there are these different acronyms. And you see some examples of, how these different vendors are designating infrastructure as a service versus PaaS versus SaaS versus FaaS and so on. Okay, a lot of time could be spent going into the pros and cons of using one versus the other and things like that. But essentially, virtualization is an important aspect. Again, vendor lock-in and all that, something that you have to worry about. Of course, operating systems like Linux are supported across these things. Lots of middleware like DB2 and CICS and such might be supported across these different PaaS platforms also. But there might be something that are supported only in a subset of these different cloud environments. And so some of these things also you need to worry about. This is no different from, oh, this app is supported in iOS, but not in Android. Things like that you have to worry about in this cloud context. There's also this notion of cloud data center architecture. People worry about trans-border data flow restrictions, and countries like India don't want Indian citizens' data to be stored in the cloud, where the cloud vendor's data center is across the country boundary. This became a problem even with BlackBerry. BlackBerry was having its data center only in Canada, US, and other places. And they were encrypting the data and storing it. At one point, the Indian government said, we are going to kick you out of the country unless you give us the key to this encryption data, or you store the data only within the bounds of India in terms of the geography and so on. So in this case, there's all this concept of, in fact, if you look at this, it will be even clearer. There's a notion of fault domain. You can have a single data center. We have multiple racks which house the CPUs and the storage and so on. Then they talk about fault domain, where multiple racks might all be in the same network connection and power connection. So if power goes away, all those guys that are in the same fault domain will be inaccessible. But in order to improve availability, even within a data center, they will support multiple fault domains. So they have independent power supplies and independent network connections. And then they'll have regional data centers. Across data centers, you also have to worry about availability, because if you come from where I live in Silicon Valley, where we have earthquakes all the time, you want to worry about if you have two data centers which are in San Jose and San Francisco, and the big earthquake that everybody anticipates sometimes is going to happens, then both of those data centers might get blown away. So you want to now, as a result, have a data center that's farther away. So that's in a so-called different region. So they also talk about availability zones. All of this has to do with what kind of SLAs you want, what is the implications of multiple copies of the data being close together or far away from each other. If they are close together, a bomb being dropped, an atom bomb being dropped in Silicon Valley will blow away all of the copies if they are all close together physically. But the benefit of them being close together is that it's faster to update the replicas. When you do an update of one replica, you can very quickly update the other replica. But if they are far away, they have higher availability, because even if one data center gets blown up or an atom bomb falls in Silicon Valley, it won't affect what happens in Manhattan. But then now the physics comes into the picture, that the speed of light and such things that you talk about normally, to talk about how much time it will take for something to go all the way to the other part of the US and come back. will be longer. And so the response time and all that will increase if you're doing synchronous replication. So there are lots of things like that that one can talk about. And then, of course, all these issues with, political boundaries and, good countries, bad countries, and things like that also come into the picture. So it all gets very complicated. So I obviously can't do justice for any of this. So I'll just very quickly talk about how, various notions have come about as requirements for this cloud context, which have to do with, in the traditional data centers, database systems and application servers and PP monitors and such required a lot of smart people to be around, and every organization that had its own data center and application development and such needed such people to be around. And there was a lot of redundancy, but also not full utilization of these resources and so on. So by going to the cloud, you get the benefit of consolidation across different vendors and different customers and such, and also, efficiencies from scaling and such, and a lot of more automated operations and much smarter people being hired and people being dedicated to dealing with one operating system environment versus another. And all sorts of stuff like that that causes cost to go down tremendously. So we talk about in this context, CapEx, capital expense versus operational expense, OpEx and all that being different based on whether you are in the cloud environment or non-cloud environment and such. And also, cost of development of the software and such. This is no different from roll your own kind of software development versus using packaged software like SAP and such. Those sorts of things come into the picture here too. And also, traditionally, IBMs of the world and even Oracle and so on had too many bells and whistles in their systems, and it wasn't always easy for the system admins or the database administrators or application programmers to figure out under what condition, what value should be set and such. Whereas now in the cloud context, they expect people to be able to get away with a lot less knowledge about these intricate details, but let the system figure out. And this is where what I mentioned yesterday also comes into the picture, leveraging AI and such things, and self-managing systems and automated ways of figuring out when the data should be reorganized and things like that. So this whole idea of dynamically also based on workload that gets put on the system, being able to bring in more resources and adapting to changes in workloads dynamically is further enabled by the cloud way of doing things than when you have your own software and hardware that you have to manage. And so this is something that can be talked about for quite a while, but at the same time, even in the cloud context, people worry about will IBM like its data to be stored next to Microsoft's data if they happen to use the same cloud. They want to, separate them from a secrecy viewpoint and such thing, just in case somebody takes over and, illegally gains access to these systems. They don't get to see the, trade secrets of the other guy and so on. So there are such considerations also which result in, and also failure, isolation and such considerations that have resulted in a lot more requirements coming into the picture in terms of how the database systems will operate in the context of the cloud way of supporting database contents and the sorts of things that you can do with those databases, and also leveraging the functionality that's provided by these different cloud vendors, and also this notion of disaggregated storage. So there are many cloud database systems that have been developed over the last, let's say, 10 years or so, but it's more actually in the last 5 years or so that the amount of activity has gone up. So if you look at something like this, the traditional database architecture, which is shown on the left with locally attached storage, everything that happens, what I showed as the component tree of a single database system, will all be executing in that node. But if you now, instead of locally attaching the storage, put it across a network, which could be a storage area network or network attached storage, NAS or SAN as they are called, or even across the internet in a cloud context, then this bandwidth, as you can see, the width of this arrow is thinner. That means that the bandwidth is less, and also the length is more. That means that it's farther away. So all of these things become a factor with respect to how you are able to handle scalability, availability, and durability. So you see here various places where you can draw this horizontal line and move stuff below the horizontal line to different node from the one where the things above the horizontal line are. So there's this notion of compute node versus storage node that's been introduced, where the compute node might be memory less in the sense that there's no persistent data there. It might still cache some data, but that's only in transient cache. So this is where things get really interesting. So unless you are a hardcore guy like Mohan who gets excited about all this nitty-gritty, gory stuff that mere mortals will be put to sleep by, I can spend many hours and all that discussing the details of some of these database systems, what they support. For instance, Alibaba Cloud, they have many different kinds of database systems, some of which focus on the OLTP domain versus OLAP domain versus NoSQL. They even support graph databases and such. So here you see PolarDB-X, which is OLTP versus Analytic DB, which is OLAP. There is even data lake analytics and so on. And even at the bottom level, you see, if you look at this, it says platform layer, and then you have the database engine, and then the utilities on top. So these are various ways of skinning the cat, if you like. And of course, the storage infrastructure is at the very bottom. Some of the details will vary based on which vendors' products you look at. But even here, if you notice, there are color codings, right? What that means is that the orange stuff is all stuff that was developed by Alibaba, whereas the black stuff is developed by somebody else, and they are hosting it in their environment, in their cloud environment. So MySQL, for instance, or PostgreSQL, Microsoft SQL Server, MariaDB, and so on are here. And then here you see HBase, and I don't even know what XPack is. And then you have Redis and MongoDB. These are two different kinds of NoSQL systems that have been around for a while now. And then this goes into the details of one of these things. PolarDB is here, right? PolarDB-X. This is now delving deeper into this PolarDB. There are many different approaches that have been taken with respect to how to provide high availability and such in this context. So people talk about normally each piece of data being stored thrice. And they also talk about copies within an availability zone versus across availability zones. And they also talk about, do you allow updates to be done only from one place and then they get propagated to the other places? And if that one place where you permit that update, if it goes down, then you allow one of the other guys to become updatable directly by the application, because that's how you provide high availability. You don't say just because the write node is down, you can only do reads of the other copies that are still available. But if you think the write node is currently down, but in fact it's a split plane problem, you're unable to talk to that write node because network connectivity is lost, but you don't know for sure whether it's just the network connectivity that's lost or in fact the other node is down. See, this is where if you can't communicate to somebody, the phone is not working, you don't know whether the other person is alive or dead. And so this is where life gets even more complicated. They also talk about how they push down tablescan to storage and use computational storage drives. So instead of just retrieving pages of data from the storage drive, you're able to push down some selection predicates and only bring the subset of the records within pages that satisfy certain requirement, like in this column, the value should be such and such. Only Tamil Nadu related records I want to bring out. And that too, people who are earning more than 1 lakh per month and so on, right? So what assumptions you make about the smartness of the file system as well as hardware. You could even have some GPUs attached to the storage node, which make certain things be done even in parallel and more efficiently than using regular CPU cores to do it. And so on and so on. So see, you already see the reference to FPGA here. They can even use the FPGA to make some of the things that go on over here be done more efficiently. But also you can talk about not using, you know, rotating storage like disk drives, but making use of directly accessible storage like flash memory, right? So all these things over time keep evolving, right? What kind of flash memory you are supporting and things like that. They even talk about in this context non-volatile memory and such. This is going further into how it processes a query by, you know, figuring out which portions of the query can be done at the storage layer versus the rest of the query having to be processed at the compute layer. So, so the concepts of distributed databases that I very briefly referred to before are shown here. What happens at the file system level versus what happens at the individual nodes where portions of the data are being dealt with. The incoming query pretends as if all the data is in one node, but the query processor at the top level, this black box, is the one that's figuring out which portion is managed by which node at the lower level. And it takes the single query and splits it into sub-queries and pushes them to the nodes that can deal with the appropriate subquery. And so this is how a distributed query execution takes place. And then you take the results from these different nodes and you combine them. And there are still some operations like sorting and so on, or duplicate elimination that might have to be done at the top level, which is called the integrated query layer and things like that. This is all, you know, lots of geeky details. In this context, you also talk about, you know, backing up the database to glacial storage or something like tape storage and things like that, in case things crap out, you know, very badly. Even your application has some bug and it corrupts the database. You want to restore to an old version of the data. Exactly where you store this backup and how many copies of it you have and how reliable is the storage. Could the storage itself over time disintegrate and cause errors in the stored version of the data? And if in addition to keeping these backup copies, you're also going to have, you know, more easily and in a faster way accessible copies of the data, because the primary node could go down and then you want the backup to be able to take over to improve availability, right? So how do you now keep the backup copy up to date? I talked about very briefly, you can send the log from the primary to the backup and let the backup keep updating its version of the data using the log. So that's what this particular approach did originally in SQL Server. I mean, they called it SQL DB, Microsoft Azure environment version of it. But there are some complications here that go into more details. But a later version, what they did was called Microsoft Socrates. Instead of sending the log, as you see here, from the primary node to the secondary node, and also the data in this case was local, right? To the different nodes, locally attached storage. Whereas in the next version in Socrates, the storage nodes are farther away from the compute nodes. So the traditional way of doing this in a shared disk architecture that we did and Oracle does the node that modifies a page by pulling the page into its buffer pool, after making the change, will push that page back into the disk storage. Whereas here, they don't do that. They actually only send the changes that they made in the form of log records to the storage server. And the storage server also keeps applying the changes to its version. And by doing this, they minimize the amount of data that gets transferred between the compute node and the storage node. So, but it introduces its own complications. So not everything comes for free because, the same data that's been modified by the first node might be asked for by the second node, which wants to read it or even modify it. If you allow in parallel multiple nodes to be able to do reads as well as writes of any portion of the database. And so if this guy already has a cached version of that page, he better realize that his cached version is out of date with the version that the other guy produced. But if he goes and asks the storage server to give the latest version of the page, the storage server might still be in the process of dealing with the stuff that has come from one of the modified guys. And it has to realize whether in the queue of things that are yet to be applied, if there is anything at all that relates to the page that this guy is asking for. You don't want to always wait till everything gets processed, because then there is a delay. So how quickly can a second node modify a page or read a page that the first node has modified a while ago is also a factor in terms of transaction throughput and response time. Anyway, I've given you a sort of feel for why life gets complicated in this kind of environment. There are more details about different systems and how they did distributed databases. In the case of SQL Server, in the case of Google Spanner, they even made use of atomic clocks and GPS to make sure across the world, when you have nodes that are operating in a combined fashion to manage a distributed database, even time synchronization becomes an issue. So there is this famous Lamport clocks algorithm that was used in various distributed systems, but that requires a lot of message passing to happen. And these guys wanted something that was even more efficient and so on. So they also, cost was not a consideration for them. So they started using atomic clocks and GPS and all that to make sure that you are able to order events carefully. That if I know that I modified this page first and then the other guy modified that page, and these things happened in two different nodes, the clocks in those nodes better not be such that the second modification gets assigned a timestamp that's earlier than the first modification, because then things will go out of sequence and clobber the ultimate state of the database. And so this is the sort of thing that you need to worry about. And also, there have been these specialist distributed file systems that have been developed. Google did it in the context of MapReduce, called the Google File System, which is a distributed file system, highly efficient, blah, blah, blah. But then they're in open source. So when Hadoop was developed as the open source implementation of MapReduce by Yahoo people and subsequently Cloudera and such startup people, they developed the Hadoop file system, which in many ways, HDFS, which is in many ways the open source version of GFS, but obviously they do have differences in terms of API and so on. So some of these differences in the architecture of these systems and what they can do, cannot do, and how good they are and so on also is affected by what kind of file system you are dealing with and what sort of operating system you are dealing with, what kind of networking technology you are relying on. In this context, even things like, what is it called? I'm even forgetting. Things like, oh gosh, RDMA, remote direct memory access, and things like that come into play, which are ultra efficient ways of from one node accessing data that's in another node. Instead of going through TCP/IP, you are able to directly go from one machine to the memory of the other machine and fetch data. But you have to do all this carefully so that security and all that is not violated. And yeah, so I think I'll stop here. There's a lot more interesting things to talk about, how to take MySQL, which was developed originally in a single node context, and then cloudify it. That's what Aurora guys did in Amazon. They kept the API the same, but they changed the innards of MySQL so that it's now suddenly operating in a cloud environment. But by keeping the API the same, they allowed you to now take your application that was a single node on-prem application that was leveraging the functionality of MySQL, but now it's suddenly become ultra modern in the sense of being able to leverage the public cloud and also have high throughput and things like that. And so, and they, in doing this, had to do some interesting, hacking of the code within MySQL to make it also fit into the rest of the stuff that's part of the Amazon ecosystem to work well and things like that. So you see in this picture Amazon S3 and things like that being mentioned, right? So, but it suddenly became highly dynamic and scalable and cheaper and so on and so on, and also network capacity requirements and all that changed dramatically. So there's a lot more details about all this here. There's too much material here. Actually, one of the guys who was behind all of this is a Tamil guy, it so happens, Sailesh Krishnamurthy, who used to work for me at one point. He later on went to Berkeley, got a PhD and had a startup. And then after a while, he went and joined Amazon, and he was a general manager for this Amazon Aurora project. So first they did MySQL's move from on-prem to the cloud. Then they did a similar one for PostgreSQL. And these are highly successful things that Amazon has done. They also did a warehouse on the cloud, which is Redshift, but that used to make a lot of money. But once Aurora came out, it started making even more money than what Redshift was doing. Then there are these new companies that are the so-called born on the cloud kind of database companies, as opposed to taking pre-existing things like DB2 or Oracle or Sybase and then making it go from a non-cloud environment to the cloud environment. So Snowflake went public and they made incredible amount of money in terms of, when they IPO'd, how much money they were able to get for the founders and such people and such. And so I'll let you guys go look at some of the references I have. Meanwhile, Apple also has gotten into the database game. So they bought something that was a small company and then they open sourced it. That's what Foundation DB is. And also there's all this effort at combining. If you thought cloud and database was, two buzzwords that got combined, now IoT also has been combined. So IoT plus cloud plus blockchain plus AI and blah, 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 all the buzzwords all put together and trying to do stuff. So here, there are a few slides that discuss how the IoT environment is being supported in the context of the different vendors' cloud offerings. And so all of this has become important, integrating smart devices and smart cities and self-driving cars and automated factories and robots and human in the loop kind of environments and things like that. So in fact, there's going to be a workshop that I'm going to inaugurate on Monday, which is part of a conference that the PSG Tech guys in Coimbatore have organized. And so the workshop is on cyber physical systems. And I'll also give a talk after the opening talk I give on cyber physical systems on blockchain as a keynote. So go look at my social media pages where you will find some of the things that relate to this. And I have to work on this presentation for the opening of the workshop. I don't know anything about, not really, but I know a little bit about cyber physical systems, but I have to say more things on Monday. Yeah.
Okay. Thank you, sir.
Sure. 1 second. Let me first get out of this. Am I back?
Just a second.
Oh, yeah. Okay. Go ahead.
Okay, I think 2 days of non-stop, things about intelligence and data. So I just want to give a little background to why we got Mohan here with such vast amount of experience from the academic side, research side, industry side, and all of that. So I've been talking to industry people, some of the industry partners. They say that, oh, PALS is arranging a session on artificial intelligence. That's not enough. You need to also talk about data, machine learning. They said they all go together. No, you cannot separate artificial intelligence from data. In the new thing, I think that's how I think Mohan summarized in the last few minutes, just before he closed. He was talking about smart cities, smart device, and all of that. So it is not enough one knows about artificial intelligence. Yesterday also talked about algorithms plus data plus compute. That's what is all new things about, right? So we're talking to the industry partners, some of them in the niche technology, in AI in healthcare, and AI and data science companies. Then actually we're talking to IBM the last few weeks. They said, why don't you have FSDP where we can combine all this in one session, 3 days. Obviously we started with cyber security. Our intention was to have something on testing. How do we test AI infused applications? AI is getting into applications more and more, whether you talk about e-commerce applications from Amazon or Flipkart. Mohan talked about columnar way of storing data. Now, a lot of data is about preferences of customers, what are they ordering? It is not related to a customer per se, but it pertains to the product and the features of the product. Now, when actually Amazon, my son-in-law is working in Flipkart, they're struggling how to deal with the millions of data about customer preferences rather than what a customer level record, customer payment, or they're not worried about customer payment at all. They're more worried about how do they innovate, which vendors should they go after, which features should they be putting it in the system. I think as students, these are all a lot of research topics for you, whatever Mohan talked about, multi-node, database, two-phase commit, all of that. These are all, a lot of things are research areas. If you Google for Mohan or if you Google for two-phase commit, joining these two, things, you'll find thousands of hits, in the Google. So, so then we've been speaking to Mohan about doing some sessions from his research of last 4 decades, some of the forefathers, his forefathers in DB2 lab, left unfinished, all of that, he has shared in the last 2 days. People may be wondering, what is the relevance of all this to industry? The relevance of industry is the future. Yesterday, he talked about AI, past, present, and future. We are all living in the present world where there are a lot of things to be explored for delivering things in the future. I think many other things are actually research areas. He has given a lot of material. And, this session was to introduce Mohan as a past, industry resource in future for any research or academic work. Mohan, he has already given his social media handle. All of you are free to access him. But PALS also will be able to channelize some of the things that you'll require. And I just wanted to share this on top of what we have been hearing last 2 days. So I just wanted to summarize and context of your 2 sessions, because all the industry partners we talk about, some of those in the new emerging area, they say CNC, just have these 2 things coming together so that they get a perspective. But still, there's a lot of areas you have to go after, and Mohan has given a lot of reference and links to those material, and he's also available anytime via his social media handle. I just wanted to add just to whatever he said, and I am not an authority on commenting on any of the theoretical or lab topic that I talked about, but I could make sense out of it for students and the faculty to further go deep dive, and Mohan is always available. If you cannot reach Mohan, call CNC. I will connect with you. Okay. Just wanted to hand it back to Robin for the rest of the sessions.
Yeah. Now we will have a Slido quiz. I have pasted the link in the chat box. Please register for the I think it is posted 5 minutes back. I think we can directly go to the quiz. I'll share my screen now. I hope you are able to view my screen.
Yes, I see Slido. Yeah.
Thank you, sir. We'll start the quiz. I hope all of them have registered. Around 100 plus participants are there. We'll start the quiz now.
I know. That'll be nice.
We have 79, 82. We give enough time to the participants, but still we are getting the message. We have not registered. We are not able to register. So please register quickly. I'm going to start the quiz. Okay, shall we start? Yes, 95 will start the quiz. Okay, your first question. Who is the father of relational data model for which a Turing award was given? You have a 20 seconds. So you need to give a right answer as well as the fastest finger. Okay, let's see. See the answer. Answer is D. Okay. The next one. Which organization people were the original developers of SQL? You have 5 options. Okay, around equal. Let's see. Answer C is the right. The next one. Which relational DBMS product was released first? Answer quickly and fastest finger also. 5971. Okay. Okay. Let's see the answer. Fourth one, which is the most important benefit of cloud versus on-prem computing? You have 5 options. Okay, let's check the answer. Answer A, only 8% right answer. The fifth one, what does split brain syndrome refer to? If you would have watched the session carefully, you would have answered. Okay. Okay, let's check the answer. Answer B. We'll see the leaderboard, who is Joshua Devasalam, Eroniction Saraswati Abhirami. Okay, let's try. You have 4 more questions. Let's move to the 6th one. Storage hierarchy refers to primarily which one of the following? Okay, answer C is the right answer. Let's move. Which one is the following list is not a cloud vendor for people outside of itself? You have 5 options. Yes. Oh, that answer A is majority of answer. Let's see the answer. Yes, that's right. The next one, which item in the following list does not refer to databases? You have 10 seconds. Okay, let's see which Linux or majority of answers. The final question, which item in the following list does not refer to a cloud service model? This is the question has come from WhatsApp. Let's see the answer. Oh, majority have answered correctly. Okay, let's see the leaderboard. Okay, congratulations, Eroniction, Akash, Marshall, Mano, Divya Kannan, Joshua, Deva Vasagam. Thanks for the participants. I'll stop my share screen. The winners, congratulations to the winners. They can switch on their video. Suppose if you have any questions, you can ask the speaker. I will unmute you.
Congratulations, all the winners.
Can you switch on the video? Those 5 people. Or you can raise your hands. Yeah, Joshua. Yes.
Hello.
Yeah, Joshua, you can ask you a question. If you have any questions to the speaker, you can ask. You can unmute yourself.
So Joshua, introduce yourself. Where are you?
Good morning, everyone.
Yeah, can you, your volume is low. Joshua, your volume is low. Can you speak up louder?
Good morning, sir.
Yes.
I'm from. My name is Joshua. I'm from Loyola IBM College of Engineering.
Where?
Loyola IBM College.
Oh, Loyola. All right. I did my PUC there. 71, 72.
Very good.
So which year are you in?
I'm in my final year, sir.
All right. Good luck. And what are you planning to do next?
I'm looking forward for my placement, sir.
Oh, okay. So you're not going to go for higher studies.
Maybe after work.
Okay.
I'm working after a year or 2. Maybe
Sure.
for the future.
Good luck.
Thank you, sir.
Other 4 participants also, they can raise their hand so that I will unmute you to ask some questions.
Akash. Go ahead, Akash.
Yeah, Eronic. 1 second, 1 second. Eroniction and to, you can unmute now. Eroniction and to, you can unmute now.
Good morning, sir. Hello, good morning, sir.
Yeah, go to your question.
Okay, I'm Aeronix and Anto. I'm from the same college as Joshua, Loyola IBM College of Engineering Technology.
Oh, wonderful. And which year are you in?
I'm also doing my final year BTech degree.
All right. And what comes next?
I've opted for placement for right now, but yeah, I'll be doing some higher studies in future as well.
Okay, I was having a harder time hearing you. You opted for, what did you say?
I've opted for placement right now, but I do
okay.
have ambitions of studying further as well.
Wonderful. All the best with making that decision.
Thank you, sir.
Okay.
Loyola. He said he's also from Joshua's college, right?
Yes, yes.
Oh,
Yes.
wonderful. Okay. Great. Are you two Chennai-based people, or you're actually from somewhere else and you're in the hostels? Anyway, go ahead. Yeah, Robin, do whatever you want to do.
Then received one question from chat box. Which cloud service provider would you choose if given the choice between AWS, Azure, and Google Cloud, and why? That is the question from Vaibhav Krishnan.
Well, I'm not going to give you answers for such questions. Clearly, there will be many differences and so on. So you have to go, just like with anything else, there won't be any one dominant thing that will sway your decision. As I said, all these vendors have different APIs. This is like asking, should I go with SQL Server or DB2 or Oracle? Asking a question in the abstract like that is quite meaningless, because a lot of the features and functionalities and so on will have a role to play in making such a decision on a use case basis. So this is true even when the APIs are standardized, right? If you use standard SQL, even then there are other features that fall outside the standard SQL which will have a bearing, which includes, of course, things like performance and availability and so on. Cost is one major factor, right? But in the case of the cloud, things are even more complicated. It's like choosing between MongoDB versus Redis and such, right? In the sense that in the NoSQL case, the APIs are different. And so it is the case with this cloud offering too. So you really have to examine carefully what the goals are with respect to your use case. And this is true of blockchain systems also. There are too many variations with respect to different aspects of the systems when you look at the different possible choices you could make. And you do need to weigh them in the context of not just your current use case, but what might happen sometime down the line in terms of requirements changing and such. So it's not a simple black and white kind of choice that you get to make. This is why, these sorts of decisions are not simple. So you have to go through a more careful thought process and all that. You'll find any number of, tables of comparisons that people will have across these different vendors. Just like I showed you couple of slides on the distributed database features of different systems. but that's just a very abstract kind of way of looking at it. But when you, and by the way, those rows that were there didn't even take into account development cost and things like that. They were only functionality kinds of comparisons. So that's my answer.
Okay, thank you, sir. Any other questions from anyone? Either you can raise your hand or you can type the question in the chat box. Till now, no questions. CNC?
Okay, thanks everyone for attending. And do go to my, I'll put it here so that you can also ping on it and get to CMO Digital University Kerala. So that's my homepage. And from there, you can get to my social media handles, and you'll see tonight or tomorrow the link to the slides of this presentation. I just have to load it somewhere. And when I load some things on Google Drive, people in China are not able to access it. So that's one of the reasons also I wanted to have the ability to post things in the Digital University Kerala website. So things like, you know, the alumni thing that we have, that's only a Gmail thing, right? It doesn't allow us to post home pages and so on in IIT Madras. So anyway. Oh, appreciate hearing that, Menaka, and good luck with everything that you guys are doing, especially since you're students and it's almost the end of the semester. Happy New Year, Merry Christmas. What else? Happy Pongal will come up soon after. I will be in Coimbatore. If any of you are from Coimbatore, I'll give the AI talk in person at PSG's. Apparently, PSG Tech has multiple campuses. I've now forgotten where. Is there a Nila campus? Huh? Yeah, that's where my talk will be. And that'll be on 23rd, which is Thursday, 2 days before Christmas at 2:30 p.m. Again, I'll post the information in my social media. I still haven't posted it. If any of you know Professor Nadarajan, he'll be my host at PSG Tech. And also, there will be more talks organized in Coimbatore. Computer Society of India, and somebody else is also going to sponsor a talk, I think. So I'll give at least 2 talks, maybe 3, on the 23rd of December and 24th of December. If anyone is in Palakkad, I'll also give a talk at IIT Palakkad on 22nd. And that'll be the AI talk, I think. Anyway, thank you guys. Happy lunch and happy weekend and all that.
Thank you. I request Mr. CNC or Mr. PVM to give any concluding remarks. Yes. Yeah, I request Mr. PVM to give a concluding remarks.
Hello, everybody. This is a hello to all the faculty and students who have actually been attending this faculty student workshop conducted by IBM over the last few days. Today, I have the privilege of sharing the same meeting room at the IIT Madras Alumni Industry Interaction Center. I have CNC, the coordinator of this event, Mr. C. Mohan, who is the speaker, and myself, another Mohan, and then we have another Mohan also in PALS. So it becomes very confusing. Looks like all the Mohans in the world are joining PALS. So coming back to the subject, it has been a real privilege to have C. Mohan from IBM USA as a part of this program. Very coincidentally, when this IBM India has been conducting this FSDP, and our Mohan also happened to be in India, and being a classmate of one of our champions, he was very keen in actually passing on his information and knowledge to our PALS colleges. And it all synchronized very well together. And we have had a very comprehensive faculty student development program over the last 3 days. In fact, over the last few days, we have also been having meetings with all the colleges. We have covered some of the colleges, some are yet to be covered in terms of our governing council, trying to understand feedback and needs from our partner colleges. And quite a few colleges have actually mentioned that they really need PALS to help them, especially with regard to emerging technologies. They feel that the faculty in the colleges are not equipped enough to teach their students about emerging technologies, and most of the information is only available through Google. So colleges are very keen whether PALS can actually provide inputs in terms of information beyond what Google can give. And it is actually by organizing such events, by getting experts from IBM to come and talk to us. And they are actually talking from experience, sheer years of experience. And such experience you cannot get out of Google information. So all the faculty and students who have been privileged to be a part of this exercise, I'm sure you'll go back with a lot of information, and you're actually being empowered and equipped in your career direction if you're interested in emerging technologies as a career. Now, as you know, we actually, as PALS, we are facilitating such programs. IBM is a key industry partner. This year, our PALS theme being to deliver industry-centric programs and have an industry-oriented content for all our programs. We have been on the lookout for key industry partners, and we really thank IBM to step up and partner with PALS as a key partner for this year. So as you notice, you're having a number of programs in terms of our industry speak lectures, as well as our faculty development program, the faculty student development program, and all that. And we'll also be following this up with an AI/ML workshop, which is actually being conducted by one of our PALS champions. We started doing this a couple of years ago. I'm sure that faculty and students would even enjoy this workshop. And we are having various other industry partners who are in the IT field, and experts from them have also been talking to us from time to time. And I must confess that I am not an IT person, and the last few years have seen great strides in emerging technologies. And I have actually retired from my profession, retired in the sense from working for a living, rather. I'm still engaged in working voluntarily. I'm privileged to work voluntarily with all of you as a part of PALS. But the point I'm trying to come to is, having listened to this lecture today by Mohan, and being a novice in this field, I must say that at the end of the session, I have got some knowledge or information. Why I'm telling you this is because there is a tendency for students and faculty to compartmentalize, saying that I am an electrical engineer, I am a computer science engineer or a civil engineer, and I need to listen to lectures only in that particular field. But what I would like to appeal to you is all students are actually you're going with the aim of either being an entrepreneur or going into industry or corporates. No problem in industry is going to come only for one particular field of engineering. So let us get out of this habit of trying to say that I am a compartmentalized engineer. Let us be a broad engineer across divisions, so that by attending lectures, irrespective of the field, whether it is core engineering or lectures on IT or emerging technologies, you broaden your vision so that in industry, when you're faced with a problem, you can have a better general knowledge and more of an ability to address the problem because of your knowledge, focused knowledge in your particular area, as well as the broad knowledge of other fields of engineering. I also thank our organizing committee from PALS for organizing this FSDP, CN Chandrasekhar in particular, our PALS champion, then Ravi, then our program management office comprising of Robin and Lavana, and all others involved in organizing this event. And keep your eyes on PALS. Keep your eyes on the events we are conducting from time to time. I'm sure there are a lot more exciting events to come. So PALS is a very excited partner. We enjoy partnering with you. Good luck and wish you all the best. Thank you very much.
Thank you.
Thank you, PVM sir.
Thank you.
Yeah, I would also like to add my thanks to everyone involved in getting this thing organized, asking me to do it when I offered to possibly give some talks and all that, and extremely well summarized discussion or conclusion by CNC yesterday and today, as well as what the other Mohan said just now. And also yesterday, KRK was involved, and Robin also has been very much after me to get my quiz information to him, in spite of all the hassles I have gone through in terms of traveling and everything. I hope at least a few of those questions were useful for you to get your act together and possibly, later go read up more and things like that. So, but the advice that was just given is fantastic. We talk about T-shaped individuals, where the vertical part of the T is the depth you have in one area, but the horizontal part of the T is where you have enough knowledge about other related areas. And over time, you can move what that depth area is by being aware of what the other areas are, at least in a minimal sense. And as time has gone on, even with the cyber physical system and topics like that, cross-disciplinary work has become extremely important. In fact, more than a decade ago, the state of California decided they were going to give more funds for research when different departments at the University of California system work together than any one department doing a project. So there was something called Citrus that they created across UC campuses that was within each campus also multidisciplinary and across campuses to leverage even, various campuses being experts in different areas, right? So in general, yeah, I mean, the name of the game now is really in the context of especially data science and such. There's even an undergraduate course that was designed at Berkeley, which was done by a committee formed across not just engineering disciplines, but even the arts and social sciences and such, business. And the idea being that there should be this one course that anyone in any major that's a student at Berkeley should be able to take. And they all need certain minimal amount of knowledge about what it means for this concept of data science and all that. And in fact, CNC was wanting me to talk about data science, but I didn't have a pre-prepared presentation. And since this was mentioned to me only a few days before I left the US and I had to do many things, I haven't signed up to do it, but I told him maybe in the future, if I prepare something like that, I can present it. So thank you very much.
Thank you, sir.
Yeah.
Any final words from CNC and Ravi, sir?
I'll leave it to Ravi because I've spoken enough. Next to Mohan, the last 2 days, maybe RKR. Okay. Ravi, would you like to say a few words at the end? We come to the end. No, Robin, I think we are fine. I think PVM nicely summarized the importance of cost discipline and
Okay.
Steve Mohan put $1 to it from California. And I think we are good. I think we should
It's
take
almost 1 o'clock.
Almost 1 o'clock. Yeah.
Thank you all. Bye-bye. Take
Bye-bye.
care. 93. That's pretty good.
Thank you. Participants, I have pasted the feedback form. Please submit your feedback form. Thank you.